things about who here actually, who has been here for more than 1 year? More than 1 year. Okay, so you're. Do you know the university ID numbers? How private are they, actually? Do people post university ID numbers on the web, or would that be considered to be a bad thing?
You mean student ID?
Student ID numbers. Are those considered private, or?
I think it's kind of private.
That is considered to be private here. Okay, interesting. Okay, so is there, but the last few digits of that would not be considered private. Is that right? Or?
I think not really. I have to call the company for free to enter that website. The password is the last 4 digits of my student ID.
Oh, so that would mean that it would be private.
I'm not sure. That should be.
Oh, okay.
It's not likely that it would allocate exactly line up.
Okay, here's the reason I am asking, and then we'll take a vote. So I'm going to be putting together the homework assignment for the 100 problem read. Okay, and I want to assign each student a different block of 100 problems to read. And so my vision was that I was going to provide a list with what the block was and some aspect of your ID number. Okay? If I gave the last 4 numbers without a name, would that be considered to be private? You're saying yes. If I gave the first 5 numbers without a name.
That's okay.
Do the first 5 numbers mean anything here? Are people going to have different first 5 numbers, you think? Because like in the United States, actually certain ID numbers, they'll have, if they give them chronologically, everybody who came in at the same date would probably have, what's the first 5 digits of your number?
0, 6. The first 2 digits indicates the year and the.
Okay. And the next after that, it's random numbers? Okay, I will play with it, but I will be sensitive to not release the last few digits. Okay, we'll leave it like that. And if we fail, we'll just talk. Okay, any questions? First of all, how did people do on the problems last week? Okay, how many people got all 4 problems from last week? I see 3. How many people got 3 problems from last week? Okay, another 1. How many people got 2 problems from last week? I see another 2. How many people got 1 problem from last week? And how many people got no problems from last week? You got none?
No. I got 4, but I forgot to.
You forgot 4, but you forgot them. Okay, good. Any questions or issues about any of the problems from last week? Okay. So today we're going to talk about the next batch of problems has to do with combinatorics. And actually, the students in the computer science program here, what do you have to take in the way of combinatorics or discrete math classes? Does anybody know? What is the, you seem like the veteran here. What courses to graduate in do you need to have in discrete math or combinatorics? So you have 1 basic discrete math class. And what book would you use in that? Or I guess you guys don't use books. Did they have a recommended book you don't read? Or by who? That's just a way of gauging what the level is. I'm just curious about that.
I think Scribble. That's for computer science.
By who? Do you remember who the book is? I know you don't read it, but who is? Okay. Anyway.
K. Bogart.
What? Bogart. Okay, Ken Bogart. Yes. Okay. So anyway, the problems for this week are on combinatorics. And sometimes when I taught the discrete math class, I'd run into people on the street and they'd say, "Oh, you're teaching computer science, and it was very advanced stuff." I'm teaching a graduate course. What are you teaching your students? Well, I'm teaching them how to count. Okay, and they usually get upset when I tell them that. But combinatorics problems are, there is a very, very deep level of combinatorics you can get up to. We're not necessarily going to get up to this here. but that to properly count certain things requires a great deal of cleverness and insight. And there's a certain number of techniques that we will be able to use. And probably the most important one I want to explain today that people probably hopefully are familiar with a little bit, but the most powerful one I think is the act of defining recurrence relations. And we'll talk about that a little bit later. But let me just review a few basic counting techniques before we get into the question of, let's say, the more serious stuff. There are certain rules, certain elementary rules for counting, which are helpful. Okay? So if you've got, for example, what they call the product rule, is if you're picking things from let's say you have some possibilities from one set and some possibilities from the other set, the question of how many pairs there are. Actually, it's kind of funny. In the United States, this is used often, the example that's usually used is what they would call a Chinese menu. Okay, and that you go to a Chinese restaurant in the United States. They often say, well, you can have a dinner where you can pick one of these from option A, from the column A, and one of these from column B, and that's your dinner. Okay, and so the question of then how many dinners can you get at that restaurant is the product of the number of possibilities in A times the possibilities in B. That I think everybody's aware of. Another rule would state that that's sort of an AND rule, okay? An OR rule, the sum rule, says that if you've got A possibilities from one set and B possibilities from that set, okay? If you want, how many ways are there for either of them to come out, okay? It would be basically A plus B. So if you've got A different pants at home and B different shirts, and you close your eyes and you randomly reach in your closet, there are A plus B possible types of clothing to pull out. And that, I think, is obvious to everyone. That sum rule has a more general, a special case of a more general world. When you're pulling things out from two different sets, okay, where they can be overlapping. Okay? So if you want to know how many elements there are in A union B, okay, it's the number of elements in A plus the number of elements in B minus the intersection of A and B. Okay, so if, let's say, what's an example of where we might want to count things that are members of two classes? Okay, someone give me an example here. Okay, let's say we want to count the number of where is a world? Because I'm going to give me two sets that can overlap. Let's give two sets in the old. Okay, so one possibility would be, a good example would be that if you want to figure out how many students there are in this in computer science, okay, it would be the union of all the students taking all the classes. In that case, it's usually more than one. That would be A union B union C, however many courses are being given. Okay? If we just count the sum of the people in each class, we will overcount, because some people will be in more than one class. Right? And if there are only two possible classes, it would be A union B minus the intersection of A and B. In general, there is a more complicated formula, okay, where you basically count all possible intersections of pairs and triples and quadruples to enable you to count how many students there would be, okay, in the union of the classes, given the relationship between every pair, every subset of classes, okay. But the trouble is that's a formula that in general is an a formula of exponential length and is not that useful once you go beyond two things. But basically, if the intersection is non-empty, then you've got to use that to count. Any questions? That I think everybody's familiar with. The other idea that I think is important in counting is the idea of a bijection. Okay, I know if you call it this and what you're used to be hearing. But a bijection is a one-to-one mapping between elements in one set and elements in another set. And the reason why this is kind of useful is it's often easier to, if you can find a bijection is somehow an alternate representation of your object. And so sometimes it's easier for you to count one side of the bijection than the other. But if there's a one-to-one mapping, that some of the things is the same. Okay? So the thing that is useful here to know about is a collection of combinatorial objects that people do know how to count. Okay? And then know that you can sort of, they exist so you can map them to it. Okay? And the combinatorial objects that I think everybody has to know. People have to know what permutations are. What is a permutation? Okay? Anybody? I know this seems probably obvious to you guys, but what's a permutation?
You get a set of elements and you get one arrangement of it.
It's an arrangement of n things without repetition. That's the important thing, is that the items are not repeated. What things in life are described by permutations? Anybody think of anything in life where really these things are permutations? Okay? Where the answers are somehow permutations. Okay? Where they arrive. Okay? Anybody encounter what? What?
Car license.
Car licenses. Well, are car licenses permutations? It's not clear to me that that's, you mean the license plate numbers? Is that what you mean?
If there are only numbers, these should be permutations. Some kind of.
If it's a number, do license plate numbers here have repetitions of digits? So if you have a license plate number, if you can get a license plate number 888, I guess that's a good license plate number here, right? Because 8's a lucky number, right? This would not be a permutation, okay, because there's repetition, okay? So if you want to count how many license plate numbers there are in Hong Kong that are legal, okay, it would not be counting the number of permutations, okay? Any ideas of anything? What? Seating arrangements. It could be a question of, right, if we have a certain number of chairs and a certain number of people in here, let's say that we have n chairs and n people. The number of orders you people could sit in would be n factorial. Because each assignment of a person, if we number the seats from 1 to n, each assignment of people to seats is a permutation. And that's a good one. What about traveling salesman tours? Let's look at one other example here. Traveling salesman problem, I think everybody knows. You've got, as inputs, a set of points. A traveling salesman tour, okay, is something that, basically a tour that visits all the points and comes back to where it is. Suppose you've got an n-city tour, okay? How many different n-city tours are there on n points, on n cities? Okay? How many traveling salesman tours are there? If I give you n cities, these cities are numbered 1, 2, 3, 4, 5, 6, 7, 8. How many tours are there? Distinct tours that visit n points. Okay? How many would there be? Okay?
8 factorial.
Well, 8, let's try n. Well, what is it? Is it n the number of points factorial?
N minus 1.
Okay. If we talked about paths, okay, there would be a path would start on any vertex. And then it is basically an arrangement of the cities. There are n factorial traveling salesman paths. But notice that a traveling salesman tour links up to itself again. Okay? And how many cyclic tours are there? You said there are n minus 1 factorial. Why is that?
Because for any cycle, n star will be the same tool.
Okay, that there's n possible shifts, if you wish, of the starting point. So what is the argument here that there are n minus 1 factorial such tours? Well, we can say that the tour starts and ends with 1. And then afterwards, it is going to be any permutation of the cities 2 to n, of which there are n minus 1 factorial. So that's how many closed tours we would count. Okay? Any questions here? So being able to recognize when there is a permutation is good because you know how to count them. Subsets, okay, are a selection of distinct elements. Okay? So if you've got n items, like here if we have 3 items, there are 8 subsets of the n items. We could have the full subset, we could have the 2-person subsets, we could have the 1-person subsets, and the 0-person subsets. Okay, so there's 2 to the n subsets of n things. When do subsets arise? Has anybody ever encountered subsets as being something that they had to count or might be something that is worth counting? Okay? Has anybody ever had an application where that has come up? Okay? I guess the number of committees that can be formed by a bunch of things would be a subset, right? Sometimes you restrict the subsets to items of a particular size. Okay? So you might consider how many subsets are there with 3 elements or something like that. But subsets are an important thing to know how to count. The other item that might be more relevant to the Hong Kong license plates are strings. A string is a sequence of items where the order matters, but the symbols are being drawn with repetition. Okay? So we consider it to be how many strings are there. If we have a string of basically n slots, each of which can be drawn from m items, how many possible strings are there? Okay, if we have n slots to fill, strings of length n characters, where each character is drawn from an m-letter alphabet, how many strings are there? What? M to the power of n, right? Because there's m of these, times m of these, times m of these are independent. M to the n. Now, what are the rules on Hong Kong license plates? Does anybody know what the rules are for Hong Kong license plates? To make a Hong Kong license plate legal? Okay, like how long they are, or what the alphabet is. Okay, in principle, it's probably the case that the number of license plates would be counted with something like this. Okay, the place where I think counting gets to be, let's say, not completely elementary, but is used, but still sort of is readily doable, has to do with things called recurrence relations. Is this what they're called here, or do people call them something different? A recurrence relation is an equation that is defined in terms of itself. The Fibonacci numbers is a recurrence relation. Okay? The recurrence relation says that the nth Fibonacci number is the n minus first Fibonacci number plus the n minus second Fibonacci number. Okay? Is everybody familiar with the Fibonacci numbers? Is there anybody who has not seen the Fibonacci numbers? Raise your hand if you haven't. You haven't, okay? How many people have heard of the Fibonacci numbers? Okay, who here has heard of the Fibonacci numbers? Raise your hands. Who here has not heard of the Fibonacci numbers? Okay. Does anybody know what they were supposed to count?
The bunnies.
Bunnies, okay? Why did Fibonacci wanted to count how many rabbits there would be. How did he use this to count rabbits? Do you remember what the argument is that this would count rabbits?
A rabbit will give another rabbit birth if it is at least 1 month, 1 month old?
Okay, well, not at least 1 month old. Okay, let's think about how you would count rabbits. Fibonacci was counting rabbits by saying that every rabbit would have babies, I guess, when it was 1 year old and 2 years old, right? So the number of rabbits would be, would be basically the number of rabbits born would be the number of rabbits in one generation, in the previous generation, plus the number of rabbits in the generation before that. Any questions? How would you count how many rabbits were born under a world where the rabbits could keep having babies every year? And rabbits never died. We didn't talk about how long rabbits died. Rabbits didn't die. And you wanted to know how many rabbits could be born. If you could give, every rabbit would give birth once a year. How many rabbits would there be after n years? What? The tooth power of this?
No.
No.
Not this.
What would it be?
There is 1 plus the square root of 5 over 2.
Okay, so you're remembering some trivia about Fibonacci numbers. But the important thing about the Fibonacci numbers is that they are generated by this recurrence relation. And this recurrence relation is important because it's about the simplest recurrence relation. This is why Fibonacci numbers occur quite often, right? Has anybody heard of any other cases where Fibonacci numbers come up in real life? Supposedly there are various things about how plant leaves grow. That the number of if you take a pine cone, if you count the number of tips on a pine cone, it's usually a Fibonacci number. And the reason has something to do because of how the rabbits grow. That somehow every pine cone tip gives birth maybe for 2 years. Okay? So, but the real reason is that this is a very simple equation. Okay? And simple equations probably occur many times. Okay? Any questions? The thing that makes recurrence relations useful is that they can often describe many, many kinds of functions by simple recurrence relations. Okay? So what are examples of simple recurrence relations? An interesting thing is that every polynomial can be expressed by a recurrence relation. Okay? So if you have something that is counted by a polynomial, okay, maybe the count is 3n to the 5 plus 4n to the 4 plus 16n to the 3. There exists a recurrence relation that will count it out. Here is a simple recurrence relation, an equals an minus 1 plus 1, where a1 is equal to 1. This boundary condition of 1, what's a2 going to be with this recurrence relation? What's the value of a2 going to be? It's 1 plus a1, which is 1 or 2. A3 is going to be a2, which we said was 2 plus 1 or 3. In general, this is a very simple recurrence relation to give that an is equal to n. Any questions about that? So polynomials are generated by recurrences. Exponential functions are generated by recurrences. So if you consider the recurrence relation, a1 equals 2, and an equals 2 to the an minus 1. a2 is going to be 2 times 2, which means a2 is going to be 4. a3 is going to be 2 times 4, or 8. This is the recurrence relation for a to the n. Does everybody see that? Every recurrence relation, that every exponential function can be generated by recurrence relations. A lot of weird functions, okay, that turn out to be interesting are generated by recurrence relations. If you consider the recurrence relation an equals n times an to the minus 1, n sub minus 1, a1 is going to be equal to 1. a2 is going to be 2 times 1, or 2. a3 is going to be 3 times 2, or 6. This is solved by an equals n factorial. Any questions? Why do I say n factorial is a weird function? Let's think about it. You may say it's not so weird. I've seen it in lots of classes. What are weird about n factorial? Okay, that makes it different than, let's say, a lot of other functions. First of all, it's weird enough that it needs its own notation. Okay, it is not a polynomial or an exponential, right? Does everybody see that? What is 2.5 factorial? Okay, does anyone know what 2.5 factorial is? Okay. It's a weird function in that it's only really defined on integers. Does everybody see that? Okay. So this is actually an example of how unusual functions, things that aren't really naturally described in the language of algebra, are in fact easily described often in recurrences. Any questions? And that's why recurrences are good things. The other thing is that it is easy to define recurrence relations in general for many counting problems, okay? And that coming to specify this equation is often not hard. What turns out to be hard is solving the recurrence relation. Okay, you were telling me here about the square root of 5, and that somehow when you talked about solving Fibonacci recurrence relation, this funny thing with the square root of 5 came in. For our purposes in here, we're not going to really worry about finding closed form solutions for recurrences. Finding closed form solutions for recurrences is a black art. It's something that certain classes of recurrences you can solve exactly in a solve to a closed form in a mechanical way. Certain other ones you require cleverness to solve. Certain other ones, like n factorial, couldn't be solved, okay, unless you have the right notation for it. So the whole question of how do you solve recurrence relations in their full generality is a complicated thing. There's this whole class of hypergeometric functions, and it's a complicated thing. But for the purposes of computer programs to tell you what the count of something is, once you have a recurrence relation, you can usually write a program to evaluate it quickly, okay, even without going to the closed form. This is one difference between this and many combinatorics classes, okay, is a lot of the time you spend studying recurrence relations, people get wrapped up in how do you solve the closed form. That is a complete non-issue to us. The ability to quickly come up with a recurrence is the issue for us. Okay? Any questions? And that's the heart of combinatorics. Okay. The most important class of counting numbers that I'm familiar with is the binomial coefficients. Okay? Where we say that n choose k is the number of ways of choosing k things out of n possibilities. Okay? So what things are counted by n choose k? Has anybody ever used the binomial coefficients to count anything? What kind of things? What?
Mark 6.
What?
Mark 6.
Mark 6. What's Mark 6? The lottery here. Okay, so what is the lottery here, actually?
49 number.
49 numbers, and you have to pick how many of them out of that? 6 out of 49. Okay? And the number of different tickets that you can buy, it would be indeed 49 choose 6. What is that? Actually, does anybody with a calculator have that? Is that a big number or a small number? It's not a small number, but how big a number is it, actually? It's kind of interesting to tell. Anybody doing it? And how much does it cost to buy a ticket?
$5.
$5. And how often do people solve it here? How often is it that you have a winner? You win $10 million.
I say that the 49 choose 6 is
49 choose 6 is approximately 10 to the 8. Is that it? 10 to the 7th?
13 million something.
Okay, you want to say 13 million. Wait.
No, I mean the choosing. 49 choose.
That's approximately 13 million, you're saying, right? And what do you pay, what do you get if you win? Does anybody know?
Around 500,000.
500,000. Okay?
No.
So this is not a very good deal, is it? Okay? So you're betting $5 on a 1 in 13 million chance of coming in, is that right? And if you win, you would get 500,000. Is that right? That seems like very, very bad odds, right? That means you have a 1 in 13 million chance of multiplying your money by 100,000 times. Okay? So it's good to know that the symbols are small. Okay? Any other questions? Okay? You can use this to count the number of ways to form a committee. That's really what you just did, right? You want to form a lottery ticket. Is a committee of 6 numbers drawn from an elite set of 49. Okay? How many paths are there across a grid? Suppose I give you a grid which is n numbers by m numbers. And you want to find out how many shortest paths there are across the grid. Okay? How many are there? You said what?
2 to the power of 2
2
and 91.
to the 2n minus 1? Well, this doesn't make sense offhand. Wait, what are you counting exactly? This number of shortest paths across an m by n grid? It doesn't include m.
2n minus 1 choose n.
Okay, what are you saying? It's going to say 2n minus 1. Choose n. That I don't know.
No, that's good.
Oh. What I would say is a little different here. First of all, there you're assuming a square grid. Here we have a grid that's n by m. Okay, so it can't be that. Okay? But what is the argument here? I think what you're going to try to tell me is that it is n plus m, choose n. Why is this? The shortest path across the grid is going to involve n downward steps and m cross steps. Right? It is a sequence, okay, of numbers where, let's just think about this. The steps are going to be numbered from 1 to n plus m. Because those are the steps, right? That's how long your path is. Of them, n of them are going to be downward steps. So the number of paths across the network are n choose this, because you have to choose what the downward steps are. Any questions about that? Okay? So that's an example of where you've got binomial about binomial coefficients. Okay? What is the coefficient of a to the k, b to the n minus k? Okay? In the power of a plus b to the n. Okay? If you expand this thing out, the way I think about it, if you have n multiplying n copies of this thing, what you're going to end up getting is each term is formed by picking one of these or one of these. And you've got n possible terms to form. Okay? The number of ways to get this term is going to be the number of ways of choosing k, of choosing a, ka's, and n minus kb's, which is the equivalent, falls out of choosing ka's out of n possibilities. And that's where the whole binomial theorem comes from. Any questions? Okay, all this we'll see, I guess, is obvious to you guys. My question is, how do you compute n choose k? Suppose, let's say that you wanted to write a program or a function to compute, okay, the value of a binomial coefficient. How would you compute n choose k? What is the value of n choose k? if you were actually going to write a program to compute it, what's the value of n choose k?
N factorial over k's factorial times n minus k. Minus k. Yeah. Minus k.
Does everybody agree that this formula gives us what the value of the kth coefficient is of the n choose k? Is this a good or a bad way to compute it, though? Bad way to compute it. Why is it a bad way to compute it? Okay, suppose, let's say I wanted to compute 100 choose 99. What is 100 choose 99? How many ways to pick 99 people out of 100? Basically, there's 100 ways, right? How to pick which guy didn't I pick. So this is something that is in principle easy to compute enough that I can compute it in my head, right? But what would this formula start out by doing? It would immediately kick it up as 100 factorial. Does everybody agree with that? And this would overflow any reasonable machine. Okay, maybe you could do it with the arbitrary precision arithmetic. But this would be the wrong way to compute it. What is the right way to compute the binomial coefficient and choose k? What? How would you do it? Pascal's triangle. What was Pascal's triangle? Does everybody remember it? Okay. In Pascal's triangle. I mean, somehow, I remember in grade school doing something like this, and you sum it up that 2 ahead of it. Why is it that this gives you? Everyone remembers Pascal triangle. That's we just sum up the 2 before it. And keep going. My question for you, though, is, why is it that this is a binomial coefficient? What binomial coefficient is this? And what does this have to do with binomial coefficient? Okay?
It is sum of the item left up by the right hand side.
Certainly it's the sum of the number 1 above it and the 1 below it. But we can just find Skiena's triangle. Skiena's triangle is going to be using multiplication instead. 1, 1, 1, 1, 1. I guess this is Skiena's triangle. Okay? It's not very interesting. It has nothing to do with binomial coefficients. Why is it that Pascal's triangle does?
It's taking the recursive formulas.
What's really the case is, if Pascal's triangle is doing, is filling things in according to the following recursive formula. There's a recurrence relation that Pascal really came up with. He said that if we number these things, what is n here and what is k? I think n is the row, right? 0, 1, 2, 3, 4, 5, right? And k is starting out here. 0, 1, 2, 3, 4, 5 in this case, right? Now, what this is now telling us is this value here is what? This is n choose. This is 5 choose 3, and this is the sum of what? 4 choose 2, and what? 4 choose 3. Is that right? So why is it that this recurrence is true? You're right that Pascal's triangle is doing this. What is the argument that this recurrence relation is true? Okay? Why is it we agree that in principle n choose k counts the number of, what did he call them? Pick 6 or Mark 6 tickets. Why is it the number of Mark 6 tickets is counted by this recurrence? Okay? Where does the recurrence relation come from?
Assume we get one ball out, get one number out, do the combination of all.
Well, the way I think about it is this. Okay, well, actually, maybe it's harder to read, but let's think about it. If we consider this to be, in the case of the balls, we have to take out one ball. Which ball do we take out? Let's say the largest of the possible balls, right? The claim here is that every subset of k possible balls from 1 to n either includes the last ball, the nth ball, or it doesn't. If it includes the nth ball, then we still have to find the other k minus 1 members of that set. Okay? And there's n minus 1, choose k minus 1. If, on the other hand, the nth largest ball is not a member of our set, then we have to pick k members from the n minus 1 remaining members. And this is where that recurrence comes from. Okay? We pick the largest value, either it has it or it doesn't. Okay? Any questions? And the beauty of this measure is, again, as we notice, the numbers are always going to be getting bigger. So we're never going to worry about overflow unless the number is too big to represent in a computer. Any questions? So here is a program I wrote, a little function I wrote, to compute, okay, the value of the mnth binomial coefficient. How did it work? I used a dynamic programming thing. I set up a matrix, okay, that was m by ny, okay. I initialized the boundary conditions. What are the boundary conditions in this recurrence relation? Okay. If you have a recurrence relation, there's the formula, which is kind of the interesting thing to figure out. And then there's the boundary conditions, which is kind of the painful thing to figure out. What are the boundary conditions on this recurrence relation?
N was larger or equal to 2.
You're saying that n is larger than or equal to 2. Well, actually, n larger than or equal to 2. That, I guess, is telling me that I guess what you're trying to say is that if it's not that, this is going to go down to 0. By a boundary condition, what I need to mean really are what are the values of this function that I know the answer of, okay? So that I don't have to compute it. It represents the end of the recurrence somehow, the stopping point, okay? You're saying that if it's beyond the stopping point, the values where these make sense, I'd better be at a starting point. What are the values of the starting points? N equals k. So if we have n equals k, that would be equal to, what is the value of n choose k under those conditions? Okay? That's 1. Okay? And what is the other value? Is the other case? Does that hit all boundary cases? Okay? And what was it? If n was equal to 0, how many ways are there to choose k things out of 0? Okay? How many ways of doing that? Okay? It is deemed that it's 1. Why is it? How many ways? Actually, is it 1 or 0? Okay? Let's think about this. This is why boundary cases tend to be tricky. What are the right boundary cases here? Okay? If we think about it, what is this recurrence relation telling us here? Again, just erase the thing. This is saying that there are choosing, you say n things out of 0. That seems weird to me.
K equals 0.
What if k equals 0? Okay? Does this make more sense? How many ways are there of choosing 0 things out of 5? Well, there is 1 here, which is the empty, sort of the empty thing. And that makes sense to me, right? So this is now the right initialization condition. And the important thing is to see that, in fact, the two terms drive towards it. Either the top value is going to get smaller in which case it'll eventually bunk into the bottom value. Or they're both going to get smaller, in which case the bottom value is going to get to be 0. Does everybody agree with that? Now we might use your case just to be also. What happens if I ask you to compute 3 choose 4? What's going to happen when we use Pascal's triangle to compute 3 choose 4? How many ways are there to pick 4 things out of 3 elements? Okay, what? How many ways are there to pick 4 things out of 3 elements? 0. Okay. To have a properly robust function, we should handle this case. This is the case that you were bringing up, right? That really what you want to say is that if the bottom one is bigger than the other one, that should be equal to 0. Does everybody agree? So here was my program using dynamic programming to compute the nth binomial coefficient. Basically, I did it in a row-by-row manner. The row goes from 1 to n. And then I computed the entire row by looking backwards to the 2 previous ones. Okay? And once I had computed all that, I had returned basically the right element. Any questions? Is this the best possible program for computing a binomial coefficient? Let's think about this. How might you improve my algorithm here for computing a particular binomial coefficient over what I did? Does anybody have any ideas? Okay, taking a look at this function. Am I using space in an optimal way? Let me look at this one. Okay, or might there be a way I could have gotten away with less space if I wanted to?
Actually, most of the time you generate all the binary number at the beginning of your program, so you always store the 2D array.
Okay, you're saying, so one thing is you're saying that if they're asking me for one binomial coefficient, they're probably going to ask me for many of them. The advantage here is that I've computed the array up to a bound. Okay? And if, let's say, this was a global variable, I might be able to reuse it. Okay? That'd be one possible way I could improve it. What if they were only asking for that one binomial coefficient? How might I improve my program? Okay? If I really wanted to. Okay? Do it as a recursive function. If I did this as a recursive function, would that be a better thing? And I will claim if I did it as a recursive function, it probably wouldn't. It would be exponential. Okay? Because notice what would happen if I did this as a recursive function. I have a structure that's looking like this. And if I don't do any storage of stuff, I just can say I want to compute this, and this, both of them are going to independently compute this node. Right? Does everybody agree with that? So if I did it without storing anything, this would actually take exponential time, and that would be a bad thing. Okay? People see what I mean? Any other ways, dimensions you might improve this function? Yeah?
Use a global 2D array to store the temporary result so that the recursive function can reuse the...
Okay, so what you're saying is, yeah, do it recursively, but before you actually compute something, see if the value existed there. Is that what you were suggesting? So maybe you would have initialized the array to all -1s. Right? And then you initialize the boundary conditions. And then when you do a recursive call, you say, if the value is not -1, report it. If it is, compute the sum of it recursively. That might be one way to do it. What would be an advantage of doing it that way? Okay, is there any advantage of doing it recursively?
You don't have to compute those useless boxes.
Does everybody see that there are some boxes that are useless here? Okay? Because if, let's say, I wanted to compute this value, okay? This value somehow, well, it's an initial condition, that's not so bad. This value here depends only upon the cells that dominate it, okay? And there might be a linear number instead of a quadratic number. So the advantage, let's say, of this approach is that if I would only calculate the values I need, okay? The disadvantage, to me, it's a little more complicated looking, but maybe I'm wrong about that. Any questions? What if we only want to compute one of these and we want to use less memory? Is there any hope of doing that? How much memory did we need for this function? Here we're using a quadratic amount of memory. Is there a way to get away with less? What? A linear array. The important thing is that because we're only looking at one level, depends only upon the previous level. We only need to keep two elements in our array, 2 rows of worth of data, as opposed to the whole thing. If we are computing it in a systematic downward way, which would not be true, I guess, if we were doing it recursively. Okay? Any questions?
And if it's really big, use the factorial formula, and you can multiply it while dividing off some factors to get out.
Okay, the other possibility you're saying, you want to try to go back to the original formula and try to do that a little bit better. Okay? How would you do it? Let's think about what you're proposing. You want to go back to n factorial over k factorial n minus k factorial. How is it you propose to do this?
You lower
The denominator.
denominator. These obviously should divide the n factorial.
Right?
And so you once you multiply one number up to n factorial, like you multiply 1, 2, 3, 4.
Right?
Once you multiply 1 up to it, you try to divide the denominator's factors.
Okay, so one possibility might be that you're saying that as you add another product here, you keep track of all the factors that you had. You basically make a list of the numbers 1 through k, and then list of numbers basically 1 through n minus k, basically. And whenever you go and add another one, you cross off things so that you don't actually multiply them. That's one way to do it, although I think the bookkeeping for that is probably very complicated. Okay? I would not imagine that that's an easier way to do it. Okay, you agree? Okay, good. Any other questions about this? So even something as simple as computing binomial coefficients is a complicated thing. Any questions? So there are several other counting sequences beyond binomial coefficients, which I think it pays to know about or recognize. The first, like I say, is the Fibonacci numbers, because they count up a lot. They correspond a lot. You know, they come up fairly often. That the number of Fibonacci rabbits born in the nth generation, okay, if we assume that there are a number of rabbits that are of length age 1 or 2, is this. How many rabbits would be born in the nth generation if rabbits were immortal? They didn't die. And rabbits could give birth any arbitrarily old. So instead of calling that the Fibonacci numbers, let's call that the Skiena numbers. What would S sub n be? Okay? We want to know how many rabbits there are born Okay? If a rabbit has the property that it can gives birth to one rabbit every year, okay? Rabbits live forever, okay? And they can give birth forever. What would that be?
You need to number times the trees is the
What?
initial number times 2 to the power.
Right, that's too complicated. I don't believe it, but if you want, you can write it down. Okay?
Well, if you say that, suppose I have 8 rabbits,
Yeah.
and every of them, each of them will give birth to 1.
Yeah.
So in fact, every year I double them.
I see.
So it's
That's okay. Let's say that. Okay, interesting. Now, what I was hoping for, and let's see if we get the same answer. I was trying to generalize the Fibonacci summation. What if we have, as I goes from 1 to n minus 1 of if Fibonacci rabbits could give birth for 3 years instead of 2, it would have been the sum of this plus f of n minus 3. Is that right? Okay? For 4 years, f of n minus 4. Does everybody agree with that? So I was going to say the recurrence I was looking for was this one.
SI.
Okay, what? Thank you very much. Okay, this is the recurrence I was looking for. Now the question that you're asking is, does it evaluate to the same thing? Okay? Your argument is what again? Tell me what the argument of your recurrence is.
So every year you, for the existing rabbits, they give birth to another. So we double them.
So you want to say that after one rabbit, every rabbit will, okay, every rabbit I see, what you're now going to give is an argument that says that any rabbit that was alive now, okay, is going to next year give birth. And that's going to double it. Okay? And the year after it keeps doubling, right? Assuming you're right and I'm right, we've just given a bijective argument for what this recurrence is. Does everybody agree with that? Okay? So I wanted this to be an example of how easy it is to change recurrences to make them count better. Okay? You're doing something more clever. Okay? The great thing about recurrence is you don't have to be too clever. Okay? You can write the formula often in a fairly straightforward way. Okay? And then automatically evaluate it. Okay? Any questions? That's interesting. The next, let's say, most advanced counting sequence that arises is something called the Catalan numbers. Do people talk about the Catalan numbers? How many people know what I mean by the Catalan numbers? Raise your hands if they do. How many people have never heard of the Catalan numbers? Okay, good. Okay? The Catalan numbers are given by what looks like a ghastly recurrence relation and has a surprisingly simple closed form that is surprisingly hard to get from here to there. Okay? So I will show you, you can assume this has a closed form. But the more interesting question is what the recurrence is and what it counts. Okay? Actually, when you look at the Catalan numbers, the way I always recognize them is when you construct 4 small examples, the number 42 always arises. 42 is an interesting number. Anybody ever read The Hitchhiker's Guide to the Galaxy? Yeah, it's a book will tell you how important 42 is if you read it. But 42, anyway, is the sign of the Catalan numbers. What is an example of something that is counted by the Catalan numbers? An example is the number of well-formed formula made by n sets of parentheses. Suppose I give you 2 sets of parentheses. What well-formed formulas are there from that? Well, from one parenthesis, it's pretty easy. It's got to be like that. Does everybody agree with that? How many well-formed, what are the well-formed formula of 2 parentheses? I could have this, or I could have that. Does everybody agree with that? What formula are there on 3 sets of parentheses? I guess I could have that, followed by this, followed by this. I could have 3 nested ones. What other ones could I have? Okay. I could have 1 nested pair, followed by something like that. I could have the 2 nested pairs, followed by this. Is there any other parenthesization I can make from 3 well-formed things? Okay? If they're counted by the Catalan numbers, I can. What's the missing well-formed parenthesization? Anybody see it? What? What? You mean something like this? Is that what you mean? Okay, good. These are the 5 parentheses. Now, how would you count the number of well-formed formula to be made from n sets of parentheses? Okay? The key idea here, as far as I'm concerned, is you have to try to find a recurrence relation. What is the recurrence relation? The important thing to see here somehow is in any one of these things, there is a first place, okay, where the left parenthesis matches the right parenthesis. Does everybody agree with it? In every one of these things, the left parenthesis matches, the first left parenthesis matches the right parenthesis someplace. And what it does then is divide the problem into 2 parts, both of which have to be well formed of their own. Does everybody see that? If we have a total of n parentheses, and there are k parentheses in this part, how many well-formed parenthesizations are there? Well, 1 pair is taken up by the bracketing. What's inside this bracket can be any way of dealing with k parentheses. And what's after that bracket can be anything that's dealing with n minus k minus 1 parentheses. So this is where this equation comes from. The number of well-formed parenthesizations is the number of well-formed parenthesizations of the k things within the first bracket times the number of well-formed parenthesizations from the things, the n minus k minus 1 things to the right of that bracket. So this is what gives rise to the Catalan numbers, this convolution, this complicated looking recurrence relation. Counts that. How many people see that? Understand why this counts parenthesizations? How many people don't see it? Okay? Let's try one more time because this is kind of cute. Okay? If we want to say that we have a well-formed formula, somehow there is a first parenthesis and it's a left parenthesis, right? Somewhere there is a right parenthesis. If it is well formed, what do we know? This part of the expression has to be a well-formed subformula on some number of parentheses. Let's say k. And this part here has to be a well-formed formula on potentially the rest of the parentheses. So how many parentheses are here? Here there were k sets. Here there was 1 set. Here there are n minus k plus 1 or n minus k minus 1 sets of parentheses. So the number of formulas is this times, basically, this times this, summed up over all possible values of k. How many people get that? Okay? It's a little complicated. But Catalan numbers arise in lots and lots of things. That's what's interesting about them. And the reason they arise is this is the simplest recurrence that involves a convolution. That's why they come up. But let's look at other examples where they come up. How many distinct rooted binary trees are there on n minus plus 1 leaves? Let's look at this. Let's say we have n is equal to 3. One, two, three, 4. Here is a binary tree, right? On 4 leaves. What's another binary tree on 4 leaves? Does anyone want to propose something else? What are the binary trees, the rooted binary trees on 4 leaves? Could have 1, 2, 3, 4. We could have what else? I guess 1, 2, what do you want? Could have 1, 2, 3, 4. Does everybody agree with that? What other ones can we have? What? Flip them? Okay, depends how you want to flip them. I can do 1. I guess I can't do anything else while separating 1 out by itself, can I? I could have a 1 and a 2 separated out. Okay, but there isn't anything else I could do with that. The other ones I guess I could do is I could separate out 4. And I could have a 1, 2, 3, 4. Is that right? Is there anything else that I'm missing? Which one am I missing? Flip this one? What does that mean exactly? Okay. What's the other one that's missing? Okay.
And a right child.
I made this 1, 2. Wait, no, I can't make it 1, 2. Once I have 1, 2, that's going to fix this thing.
That's in here.
What? Going to have this one here be 2, 3. Is this what I've got? Does everybody agree with that? Those are the 5 trees. How do you go back? This is painful, and I would have made the mistake, but I've got 5 of them. How would I count how many binary trees there are on n such things? On n plus 1 leaves. Okay? If I want to come up with a formula here, is there any kind of an argument that I can do, a recursive argument, to count these things? Yeah?
Remove the root and then recursively do the multiplication of 2 trees.
Does everybody agree that if I take off the root, okay, the good thing about the taking off the root is that I am left with 2 subtrees, okay, and because it is rooted, the numbers don't shift around, right? It's a partition of these things. So how many trees are there rooted with k things in it? Okay, where I have n things in it, binary trees? Well, once I remove one element, if you think about it, what's kind of left here? Here, I originally had, if there are k things on this side, the number of rooted of trees that I'm going to get is the product of the number of ways on this side times the number of ways on that side. What is the number of ways on each side? Let's think about this a little bit carefully. Here, if I have the first numbers 1 through k, there's c to the k ways to finish this one up, because now there are k leaves. How many leaves are there on the other side? How many leaves? Okay. There were n minus 1, n plus 1 minus k. We've taken that thing off, and that is what? C to the k to the n minus k plus 1. Okay? That's exactly the same problem. It's exactly the same recurrence as we had up here. Excuse me. Okay? Any questions? How many triangulations are there of a convex polygon? This is an interesting one also. Here I have a 5-pointed sided polygon. How many ways are there to carve this thing up into triangles? Okay? Basically I'm allowed to use chords that span this thing. How many ways are there to do it? Okay? If I want to, here is an example of one, right? In this particular instance, how many ways are there? Okay, 5, right? Because in this case, once I have 5 points, there's only one possibility, okay, for the star point. Is that right? In general, if I give you an n-sided polygon, numbered from 1, 2, 3, 4, 5, 6, 7, how many different ways are there to partition this into triangles? Okay? We need a recursive idea to count this thing. Okay? How many ways are there to partition this thing? How many people are confused by what I mean by a triangulation? Okay? Who here understands what I mean by a triangulation? Okay? Most people. Okay? How do we get the recursive idea here to count these things? Okay? There's kind of this idea that if we divide this polygon into parts, the number of ways to do it is the number of ways of triangulating this side times the number of ways of triangulating that side. That I get. But what is the way that we triangulate this into parts? What is the idea that we would like? Okay? Any ideas?
Fixing one point and linking it to another point.
Fixing one point. So one possibility is you divide it with a chord like this. Is that right? But which chord is it? Why is that different than if I ended up... How do I avoid double counting it? Because sometimes I might divide with this chord, but I also had divided it with that chord. Okay? So the idea that actually I think is the one that's most obvious is what if we realize that this first edge has to be in a triangle. Okay? What do we know about there's 2 points in the triangle that contain this edge. How many other points are there in the triangle that contains this edge? How many points are in a triangle? 3, right? 2 of them are specified. 1 of them isn't. Does everybody agree that this edge, 1, 2, is going to have to be in a triangle where the other 2 points are going to be shared on one vertex? Does everybody see that? If so, how many ways are there to divide this thing to finish the job? The number of ways here times the number of ways there. Does everybody agree with that? So in this case, where does the Catalan recurrence come from? We're going to divide up the edge between the first and the second points. There are k possible intermediate. The intermediate point that's paired up with it is k. Once we have that, there are now k points in this triangle, and n minus k minus 1 points in that triangle, in that polygon. Okay, and the product of that does the job. Any questions? So Catalan numbers are a useful counting sequence for lots of things. Any questions? Okay, let's move on and look at the problems of this week. Okay? There are 4 problems. The first one, okay, has to do with counting n. You want to express how many ways are there to make n as the sum of integers, where you've got 1s, You've got 2s, 3s, and 2 flavors of 1s. Let's call them 1 and script 1, 1 prime. Okay? So how many ways are there to make the number 3 from the sum of things that are 1s, 1 primes, 2s, and 3s? How can we make 3 as the sum of these things? Okay? 3 could be just the sum of 3. It could be the sum of 2 plus 1, 2 plus 1 prime. Or it could be the sum of 1 plus 1 plus 1, or 1 plus 1 plus 1 prime, or 1 plus 1 prime plus 1 prime, plus 1 prime plus 1 prime plus 1 prime. Does everybody agree with that? So the question is, count how many ways that can be done. The second problem asks you to count how many ways there are to build a well-formed formula. So you might be smelling Catalan numbers already. But there is an extra parameter that the formula can't get D levels more than D levels deep. So if D is equal to 3, this would not be a legal parenthesation. And the question is, count how many ways there are of doing that. Okay? Any questions? The next problem asks you to solve a 4-peg Tower of Hanoi problem. Did everybody solve the Tower of Hanoi problem does everybody know what the Tower of Hanoi problem is? You know, in the story of the Tower of Hanoi, at least as it was supposedly written, there was 3 pegs. You had these discs. They sat on 3 pegs. Okay? And you had to move them from here to here without ever having a big peg on a small peg. That was easy once you understood how to do it. A much harder problem is, what if you have 4 pegs? Okay? Now move all the discs from here to here, using as few moves as possible. The interesting thing is, actually nobody really has proven what is the best way to do this problem. Okay? But in the problem they give you a proposed strategy. And the question is, find the best strategy from that class of strategies, which likely is probably the best way to do it. Any questions? And the final one is kind of a cute one. There is a sequence which is, we're going to call a self-describing sequence, which has the property that it consists of the numbers from 1 to infinity. It's an infinite sequence. And what it is the number of, it's in order, so there's no, it's a sorted sequence, so there's no doubt about what it is once you have the specification of the values. Basically, f sub n, in this sequence there are f of k values of k for each k. So in this case, there is, if k is 1, there is 1, 1. If k is 2, there is 2 2s. So that means they've got to go here and here. Now we know what 3 is, so that tells us how many 3s there are. 1, 2, 3s. This is in the 4th spot, so how many 4s are there? 1, 2, 3. This is in the 5th spot, how many 5s? 1, 2, 3, and so on. And the question is really, what is the value of the ith value of this sequence? That's what you're asked to compute. Any questions? Any questions about any of these? Okay, think about them, and we'll talk about them next class. Okay? Thanks for your attention.